Welcome to Cambridge IGCSE Physics, Lesson 8.1, Turning Effects. Moments. Today we explore how forces create rotation and turning effects in everyday objects and engineering systems. Let's examine our learning objectives for today. By the end of this lesson, you will be able to first, describe moment as a turning effect measure, understanding how forces create rotation. Second, give everyday examples of moments, recognizing turning effects in daily life. Third, understand what causes rotation, the physics behind spinning and turning motion. These objectives align with Assessment Objective 1, focusing on knowledge and understanding of fundamental physics concepts. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, moment, pronounced moment, which means the turning effect of a force about a pivot point. Second, pivot, which means the fixed point about which rotation occurs, like a hinge on a door. Third, perpendicular distance, which means the shortest distance from the pivot to the line of action of the force. Understanding these terms precisely is crucial for solving moment problems and analysing rotating systems. Let's explore our first core concept. What is a moment? The fundamental principle states that moment measures the turning effect of a force about a pivot point. This means how effectively a force can cause rotation. The definition is moment equals force multiplied by perpendicular distance from the pivot. Mathematically, we express this as moment equals force times distance, where force is measured in newtons and distance in meters, giving us units of Newton meters. The diagram illustrates a simple lever with a pivot point, showing how force F applied at distance d creates a turning effect. Notice how the distance is measured perpendicularly from the pivot to the line of force action. This principle is fundamental because it explains how tools like spanners and levers work effectively. Now we examine the experimental method for investigating moments. This follows Cambridge IGCSE standards. The apparatus needed includes a meter rule marked in centimetres, a pivot or fulcrum, various masses of known weight, and mass hangers for attachment. The method consists of these steps. First, balance the meter rule on the pivot without any masses. Second, add masses at different distances from the pivot. Third, adjust positions until the rule balances horizontally. Safety is paramount. The hazards include falling masses causing injury. Therefore, you must secure the pivot firmly and position hands to catch any falling masses. The diagram shows the experimental setup with masses at distances d1 and d2 from the central pivot. Notice how we measure distances from the pivot centre to each mass position. Let's work through our first example. The problem states, a spanner applies 50 newtons force at 0.2 meters from the bolt centre. Calculate the moment. We are given force equals 50 newtons. Distance equals 0.2 meters. We need to find the moment in Newton meters. Step 1. Write the equation. We use the moment formula, which is moment equals force times distance, where force is in newtons and distance is in meters. Step 2. Substitute the values. We write moment equals 50 newtons times 0.2 meters. Step 3. Calculate. 50 times 0.2 equals 10. Step 4. State the answer. The result is 10 Newton meters to two significant figures, demonstrating the turning effect of the spanner on the bolt. Example 2 applies the principle of moments to balance forces. The problem is, balance a 2-meter rule with 3 Newton and 6 Newton forces applied downward. The data shows left force is 3 newtons, right force is 6 newtons. Now we analyse. First, apply the principle of moments. For equilibrium, clockwise moments must equal anti-clockwise moments. Second, set up the equation. 3 newtons times d1 equals 6 newtons times d2. Third, use the constraint that d1 plus d2 equals 2 meters. Fourth, solve simultaneously. From the moment equation, d1 equals 2 times d2. Substituting, 2d2 plus d2 equals 2 meters, so d2 equals 0.67 meters and d1 equals 1.33 meters. The diagram shows the balance system with forces creating equal and opposite moments. Mathematical skills are crucial in moment problems. Let's examine 3 key skills. First, the principle of moments. For any object in rotational equilibrium, the sum of clockwise moments must equal the sum of anti-clockwise moments about any point. This applies to systems with multiple forces acting at different positions. Second, perpendicular distance measurement. Always measure the shortest distance from the pivot to the line of action of the force. If the force acts at an angle theta to the lever arm of length r, the perpendicular distance equals r/s sine theta. Third, sign convention. Choose either clockwise or anti-clockwise as positive, then apply the opposite sign to moments in the other direction. Consistency in sign convention prevents calculation errors and ensures correct equilibrium analysis. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, a force of 20 newtons acts at 0.3 meters from a pivot. Find the moment produced. This tests direct application of the moment formula. Question 2 is intermediate. It states, balance a 4 Newton force at 0.5 meters with an unknown force at 0.2 meters. This requires you to apply the principle of moments we've learned. Question 3 is advanced. The question is, a door handle 0.8 meters from the hinge needs 15 Newton meters moment to open. Find the required force. This tests your analytical skills in rearranging the moment equation. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Physics principles power our modern world. Let's see how moment concepts apply in practice. In engineering, crane design relies heavily on moment calculations to ensure stability and prevent toppling when lifting heavy loads at various distances from the base. In architecture, building structures must be designed to balance against wind forces and seismic loads using moment analysis. In everyday life, simple tools like door handles positioned far from hinges, bottle openers that multiply applied force, and scissors that cut efficiently all demonstrate moment principles. These applications show why physics matters. Career-wise, moment knowledge leads to mechanical engineering, designing machines and tools, structural engineering, creating safe buildings and bridges, and robotics developing precise movement systems. The concepts you learn today become tomorrow's engineering solutions. Let's review the solutions. For question 1, the answer is 6 Newton meters. We calculate moment equals 20 newtons times 0.3 meters equals 6 Newton meters. This is reasonable for a moderate force at short distance. For question 2, we apply the principle of moments. 4 newtons times 0.5 meters equals unknown force times 0.2 meters. Therefore, 2 Newton meters equals F times 0.2 meters, giving F equals 10 newtons. For question 3, we rearrange the moment equation. 15 Newton meters equals F times 0.8 meters. So F equals 15 divided by 0.8 equals 18.75 newtons. Now, exam success tips. First, always show you're working step by step. Even if the final answer is wrong, you earn marks for correct method. Second, include units in every calculation step. This demonstrates understanding. Third, check if your answer is reasonable. A door shouldn't need 1,000 newtons to open. Fourth, read questions carefully, identifying given information and what you must find. Let's summarize today's lesson. The key points to remember are: first, the definition of moment, as force multiplied by perpendicular distance from the pivot, measured in Newton meters. This quantifies the turning effect of any force. Second, the principle of moments states that for rotational equilibrium, clockwise moments must equal anti-clockwise moments about any point. This principle allows us to analyze balanced systems. Third, applications of moments appear everywhere, from simple tools like spanners and scissors to complex engineering structures like cranes and bridges. These 3 concepts form the foundation for understanding rotational mechanics. For further study, practice moment calculations with various examples to build confidence. Work through balancing problems involving multiple forces. The next lesson covers center of mass, which builds on today's work by exploring how mass distribution affects stability and balance. Ensure you understand moment calculations before moving forward, as these skills are essential for advanced mechanics topics.